So let's look at some of the reactions with dienes. First, let's review. How do pi bonds react? Well, we remember from the very first one of the first reactions we've learned, chapter 8, we had an alkene. The pi bond reacts with, being electron rich that is, reacts with a partial positive of hydrogen halide, like this, right? So remember, because of this dipole. So nucleophile attacks electrophile, releases this as a leaving group. All right, that makes a carbocation. So before we get to this, we would first end up with a positive charge on the more stable position, the secondary or tertiary position, not the primary. And then you have the bromide ion come in and act as the nucleophile in the second step, then leading to this product. Now when we have double bonds, we have the same kind of reaction, but it's a little bit more complicated because we have two alkenes that can react, right? You have two pi bonds that can react. So let's see how we get both products. The first product you get is where, let's take a look. It's reacting at this double bond right here. So you can imagine this is going in, attacking the H. We make the positive charge right here, and then the bromide comes in and attacks there. And so that's how we get that product there. This is what we call the 1,2 adduct, because if we number our carbons 1, 2, 3, 4, we have the addition at 1 and 2. How do we get the 1,4 adduct though? So how do I get the reaction at carbon 1 and then all of a sudden I have a reaction at carbon 4? There seems to be this weird disconnect, right? Well, let's show how that might form. First, let's transfer this idea down here where it's meant to go. Now for the 1,4 reaction, let's take a look at what's going on there. So I've got this starting material and we had numbered it this way. Doesn't really matter as long as we keep it consistent. I would say we want to use the same idea, but then just think about how one little change during the reaction can give us this other product. So let's maybe start out the same way. Now here's where something different can happen. We notice that instead of bromide coming and attacking here, it ends up attacking at carbon 4. So do you guys see how or why it would do that? So at this stage, maybe some of you guys see the resonance structure that would occur, but that would put a positive charge here. Now, two schools of thought here. One is you could have resonance there because this is allylic stabilized, right? So we have not just any kind of primary carbocation, this is allylic primary because it's next to a double bond. There we go, I fixed it. Okay, so this moves over here, and then that puts a positive charge there. So because it's not just regular primary, it's primary allylic, this is okay to have, which means then the bromide can come and attack here. And that leads to our 1,4 product up here. Another thing you could do is have the bromide attack right here and move that pi bond over to here. Either way is fine. So let's take that idea and apply it to this problem. Now we have a cyclic diene. Go ahead and show me what is the 1,2 and the 1,4 adduct, and show me the mechanism as well. So the first step is going to be take either of these double bonds and attack HBr with it. Now you have two options for what you end up with. You're either going to have the positive here or the positive here. I think you guys know the positive prefers this position because it's tertiary. That means the H is right here. Now the Br can attack here and we get the 1,2 adduct then, correct? Now to get the 1,4 adduct, I just need to consider the resonance structure here. So the resonance structure is to move that there, and I get this carbocation, which is allylic, and then the bromide could attack here. If bromide attacks there, what will I get? I'll get the 1,4 adduct, which means the bromide is down here, and I have this, and the H is position 4 away. 1, 2, 3, 4. This is the 1,4 adduct. And I'm going to go ahead and number these carbons since you're learning about this. I'm going to number them 1, 2, 3, 4. plus this is my 1,2 adduct, or this is my 1,4 adduct. And then just a variation of this is instead of HBr, if I had Br2, it'd be the same thing, but instead of an H and a Br, I'd have a Br and a Br. And you see the same thing, a 1,2 versus a 1,4 adduct. That just tells you where these groups added if you number a carbon chain. All right, so let's review this reaction. It's been a while since we had Br2, right? So I'm going to show it reacting over here, but it could just as well react over here. So this is symmetrical. If you recall, the pi bond reacts with the bromine. Let's go with that. But this is large and polarizable. With its lone pairs, can come back and attack as well. So we can avoid a carbocation here by making this cyclic. So that is, we're going to have a cyclic bromonium ion, and we release bromide ion here. So this is what we're going to have. So this makes a bond here, and it makes a bond back. So it makes this triangle. Now, we usually have bromide attack. This is Markovnikov addition. This is all driven by electronic factors. So the more stable carbocation-like transition state is where you attack here. So it's going to have a lower activation energy than attacking here, because this is more stabilized as a partial positive charge, because it's greater substituted. So this is going to give me this pattern here. And let's not forget, this alkene here did not react, so it's still there. Okay, now let's see if we can explain the 1,4 adduct here. The 1,4 adduct, I think you could explain it this way. You could either have resonance here, or you could have this attacking here. So that attacks there, and then you could get that. So that's the blue arrows are gonna lead us to a ring opening as well, but you're gonna have the bromine attack at carbon 1 if I number it this way. Or actually, I guess I should number it the other way. This is the 1,2 adduct. This is the 1,4 adduct. So that's assuming I was numbering it this way. All right, now for major versus minor, notice that there are two different outcomes. You could either have the 1,2 adduct be the major product when we have lower temperature, or at higher temperature you can have the opposite. So this is very much temperature driven. So first, some vocabulary. The less stable alkene is going to be called the kinetic product usually. Okay, so if I look at these products, I have a mono-substituted alkene, and here I have a di-substituted alkene. So the one that's less stable is called the kinetic product, whereas the one that's more stable is called the thermodynamic product. So that's usually purely based on the substitution pattern of the alkene. That is, I'm looking at this alkene and I'm saying how many R groups are on it. There's one R group here. Looking at this alkene, there's 2 R groups on that. So this is going to be more stable. Now at higher temperatures, the thermodynamic product is favored, and at lower temperatures, the kinetic product is favored. Okay, so let's write that down. So let's try to explain this with some energy diagrams. So let's look at the energy diagram. If you take a look here, notice that the diene has a certain energy, and then we make this carbocation is the intermediate here. And if you think back to the carbocation in these examples, they're resonance stabilized, so they're both pretty stable. So usually that's going to be the same energy here. Now Hammond postulate would say that this energy of the transition state is going to be closer in energy to this than to this. So this is going to usually be dictated by the energy of the intermediate. If the energy of the intermediate is about the same, regardless of the pathway to either product, then how come these activation energies are so different? Well, that then has to do with something called the proximity effect. If you look at this reaction here, remember this attacks here, this gets let go, we make a carbocation, and then you could have this either attack here or attack here and push these electrons there, or have the resonance occur and attack here. Well, proximity effect says it's faster if the bromide attacks here because it's already there. Okay, it just dissociated where right here, so then now it just attacks. All right, so that explains why the kinetic 1,2 product is going to have a lower activation energy, because it's observed to be faster. So relatively speaking then, the 1,4 adduct has a higher activation energy as a result. Now what does this have to do with temperature? So the less energy you have available because you're running a reaction at lower temperature means you're more likely to take the pathway with the lower activation energy to begin with. So that's going to be the 1,2 adduct. So this is going to be favored at low temperature because you can achieve this activation energy at lower temperature. However, at higher temperature, the thermodynamic product is favored. Now you might wonder, well, if I have higher temperature, that just means I can get both of these, right? Well, it turns out that at higher temperature, that means you're more likely to be able to reverse your reaction. So let's say you have a certain amount of energy and you can overcome this first barrier, and let's say you just happen to overcome the second barrier like that. Well, at higher temperature, you're more likely to be able to reverse and then meet this energy requirement and go down to here. But you're less likely to go back all the way up here again to go back to here, right? So you're more likely to be able to reverse the kinetic product and meet the extra energy you need to get to the thermodynamic product. But this activation energy for the reverse for the thermodynamic product is much higher than the reverse activation energy for the kinetic product. So you're more reversible for the kinetic product to form thermodynamic product and less reversible for the thermodynamic product to form kinetic product. So basically it's like you're pooling into an energy sink, right? Everything forms eventually into the thermodynamic product, and it's harder for the thermodynamic product to get out of that and form kinetic product. So let's use these as an example. So here I've got HBr and I've got 40 degrees C, which I'm considering high temperature. So here the more favored product at higher temperature is going to be the thermodynamic or more stable product. Again, because you're more likely to reverse from a kinetic product into a thermodynamic product than the other way around, due to the reverse activation energy being much higher for the thermodynamic product than the kinetic product. In other words, if I were to form kinetic product, it could easily reverse at higher temperature, but the thermodynamic product has a much higher reverse activation energy, so it is harder to reverse. So as a result, I end up with more thermodynamic product. So here, I'm going to have the thermodynamic product be my major product, and that means it's going to be the 1,4 adduct. So to get that easily, I could do the mechanism, of course, or I could just number this and put my H here, and put my double bond here, and put my Br here. Now, how do I know the double bond is here when I started off with the double bonds there? Well, that's from the mechanism. So I'd have to think about grabbing the H, making this the positive, and then doing the resonance structure and putting the Br down here. So you can see that there's going to be a resonance structure there. Go through the mechanism if you're not sure. We worked it all out up here before. Okay, for the next one, this is going to favor the kinetic product because we're at a lower temperature. So I'm going to favor the 1,2 adduct as my major product, which means if I do 1, 2, 3, 4, again this is symmetrical, I have H at 1, and I have Cl here, and I have the resonance structure putting the pi bond there. All right, and if you guys want as a challenge, try a molecule that's not symmetrical, so I could easily adapt one of these into an example like this, where now this double bond is different from this double bond, and see what you would get there. You get different possibilities now. Go ahead and work that through. What would your major product, what would all your possible products be? and which would be your favorite at high temperature and which would be your favorite at low temperature. All right, guys, so for this one, it's a bit of a mess, right? You have so many different possibilities. Basically, my strategy would be, do the same thing you did before when it was symmetrical, but just see what all your possibilities are. So first, just pick one double bond, okay? So I'm just going to pick this one, doesn't matter which one, and do your 1,2 addition. So if you take a look here, I did a 1,2 addition here, and I put the X here because that's where the carbocation would be. And then I did the resonance structure and added the X here because that's the 1,4 position. But this was still based on originally reacting the double bond that was here. Now, in a different color, let's consider the two products if I react this double bond with the HX. Then I can get this HX addition here, or because these are both secondary, perhaps the carbocation reversed. Maybe I added the H over here and the X over here, right? Because the carbocation is equally stable. Well, actually no, because this is the allylic position, right? So yeah, actually I need to have the positive charge here because it's next to the double bond. So they're actually not the same. So you have to think about things like that all the time. So, just draw them all out, cross it out. If it doesn't work out, it's totally fine. So now let's try the resonance structure then. So if I had a carbocation here, this double bond could move down here and the X could add up here. So how many different alkenes do I have? I don't just have one 1,2 adduct and a 1,4 adduct. I have 4 possible adducts, one for each pi bond that reacted. So I got the 1,2 adduct here and the 1,4 adduct here from this double bond reacting. Now I reacted that one. I have a 1,4 adduct, or 1,2 adduct here, and a 1,4 adduct here. And then you want to just look at them again and see if they're different from each other. Clearly, this has an X on the methyl group carbon, so that's a unique structure. These guys here, I think, are considered the same molecule. And here it depends on the chirality. This is the chiral center, but we're going to get the enantiomer because it's a carbocation, so you can have a tack on either side. So these I would consider the same molecule, and you're going to have enantiomers of both of them. Or they're the same molecule. So you're going to have this plus the enantiomeric pair of those. And then here, you're going to have the same thing as here, right? So it turns out that you end up with these 2 products anyway, plus the enantiomers of these. So 3 products total. And to answer my question about, which one's favored at low temperature, we would say it's the 1,2 adduct, the kinetic product. And why is that kinetic? Because I have a di-substituted alkene here. And then here, this is my tri-substituted alkene, so this is my thermodynamic product. And you always want to just double check because it could reverse. Maybe the alkenes are similar stability, and so you don't see a really big difference. So just always confirm with the double bond. If you see more substitution or less substitution, that can indicate differences in stability.